Next, I'd like to switch gears and introduce you to today's keynote speaker. He's an internet security industry veteran and a business entrepreneur who's been a driving force of secure online innovation for the past 30 years. He's the inventor of the Elgamal digital signature scheme, which is the basis for the digital signature algorithm. While serving as chief scientist for Netscape Communications, he was the driving force behind SSL. And in 2009, he was the recipient of the RSA Conference Lifetime Achievement Award. Please join me in welcoming Dr. Taher Elgamal, the Chief Technology Officer responsible for security for Salesforce. Taher, the podium is all yours.
Thanks, Frank. Good morning, everyone, and thanks for joining us. As Frank noted, I have been in cryptography actually for 40 years, and I spent the majority of my career in different aspects of it. So I would like to just share views from where cryptography came from, where is it trying to go to, and what is the current usage, and so on. And I'll outline how MPC is actually one of the very promising technologies that are being worked on now. It's easy to note that 25 years ago or so, or maybe a little longer, when we decided to use the internet for e-commerce activities, actually, one of the very first things we did is, how do we secure data traveling over an open network? Which was a good question. And the answer to that was the use of cryptography, because we knew that you could achieve confidentiality, you could achieve authentication, and you could achieve integrity with different cryptographic methodologies. And the use of cryptography is actually through the SSL and then TLS protocols, basically has been the backbone of everything we've done. There's a lot of security issues that we have now in conducting commerce over this public network. But actually, the use of that protocol or these protocols has sort of survived the years, and is enabling, trillions of dollars of transactions every single day these days. So the use of cryptography has been quite important. And if you look at, all of the other security controls that we have, it's easy to argue that cryptography is actually the one thing that is extremely scientific in terms of building and continuing to use this public network. Cryptography needs to change with the modern times. There's a lot of new requirements that we see, and I'll touch on a little bit of what the new areas in cryptography look like. So this is kind of easy to look at. We use TLS for almost all e-commerce activities. We use IPsec for connecting into VPNs and so on. All of that is using cryptography, of course. Encryption at rest is becoming a really interesting thing. You see a lot of different regulations and so on requiring encryption at rest. And then the Bitcoin, the digital currency world that grew up several years back, is actually based on hashing and signatures and so on. So it uses cryptographic algorithms. And then there is the wonderful IoT world, which actually is changing things rather dramatically because the number of nodes on this one public network is growing exponentially. There's cryptography everywhere. Why are we having this conversation? There's a lot of challenges. That backbone was designed literally 26, 27 years ago. And it was built in a world where we were just starting out. If you look at the TLS or the SSL crypto specifications, there is some agility associated in it. So you can actually change the cipher suites and upgrade things and increase the key size of encryption methods and so on. But the digital certificates do not have any agility. So when we had to change the hashing algorithms from MD5 to SHA-1 and then from SHA-1 to SHA-2, it actually costs everybody millions of dollars and a lot of hours. So the use of digital certificates has proven to be extremely useful because that's how we establish the trusted relationship between the client and the server. But the lack of agility there is actually cost everybody so much. And it's interesting to note that that will continue. There is no crypto algorithm that will survive until the end of time. We have to actually plan on a different world. Vulnerabilities in code have cost us a lot. I remember the Heartbleed security bug in OpenSSL several years ago, and everybody was just calling everybody, where is our SSL? What do we use? I mean, people did not actually know, because the implementations in most enterprises are not actually explicitly saying we use this library or not, or we use even this algorithm or not. So there's a lot of missing information, unfortunately. There is a thing that we actually knew when we first started e-commerce, which is it all is landing on what happens if RSA breaks. So the root of trust in all of e-commerce is a number of RSA keys that belong to the different certification authorities. These are embedded in browsers and other clients, if you wish. But if RSA were to actually be broken, quote unquote, then somebody can sign anything and claiming to be anybody. So the trust just basically completely goes away. All digital certificate will be untrusted, and that would be a lovely world to actually see. Now, we actually knew that was a problem in the beginning, and we discussed, what if we double sign things and that kind of stuff, use different algorithms on top of each other? And we just decided that was not going to be a very practical thing for performance and bandwidth purposes. But we do have that issue still. Storing keys is a fantastic thing, because there's a lot of things we tell people about what to do and what not to do. But there is very little guidance on how do you actually run a web server if you're terminating something at a web server and there's a private key that is establishing a session. And it turns out if a hacker or some ill-intended person could find where the private key of any connection is, they can actually unravel that entire connection, and that data is basically not secure anymore. And we don't talk about that a whole lot, but it's actually probably the most important thing in terms of cryptography in the security world of today. Digital currencies kind of choose whatever they want in terms of cryptography, and although it's actually surviving today, that there is just nothing that says that if you use this crypto method now, what happens in 5 years. And there are best practices that the crypto community provides to the world that says these are the methods that would like you to use. But these digital currencies kind of choose their own. Things are changing, and I'm sure everybody's heard about the quantum computing challenge that we have, that public key algorithms that we use today are likely to get broken when a big quantum computer exists. That might be in the next 10 or 20 years, depending on who you believe. It's not really known, but it probably will happen. That actually makes the current information vulnerable, because if I record an encrypted session and just sit on it until RSA is broken, I can decrypt it. And when I decrypt it, I'll find out what that conversation was. And, if it's my credit card number, probably doesn't matter because it's changed. But if some useful information, a lot of information is still valuable in 10 or 20 years. And you know, the digital currency world will probably suffer as well, because if the signature algorithm is broken, which is ECC or any other signature method, if that is broken, then I can sign something. So I can actually convince the system that a transaction happened, and I can steal money effectively. So NIST has been running this post-quantum standardization process for the last few years. So far, they have 7 finalists, and they mostly use this lattice crypto scheme methodologies. There's some others. And it looks like we are going to arrive at a number of algorithms that will be resistant to quantum computing. But we do need to keep track of the fact that these are not going to be fixed after either. So the agility has to be maintained. There's a number of new technologies that people talk about, and it's kind of worth discussing here. Homomorphic encryption is a set of promising encryption technologies that perhaps one can use to conduct operations on the encrypted data without having to decrypt it. So you can maintain the confidentiality, but run your AI method or machine learning or something like this. MPC has more applications, and I'll get to that in a second here. But MPC basically makes the storage of the private key, for example, a lot better in terms of security, because the key gets separated between multiple hosts. And then there's the whole confidential computing with Intel and so on, which is actually useful because you can run your encryption methods in a protected area in the processor. MPC tries to basically make each cryptographic operation separated into 2 or more environments, so that nobody can actually get the entire key unless you find access to multiple machines at the same time, which is obviously a lot harder. So, you know, the financial services companies have adopted almost MPC in a lot of different areas. Mobile user authentication is kind of interesting because you can actually run an authentication from a mobile phone to a server without having to store the key on the mobile phone, which is kind of intriguing. HSMs, which is the hardware security module, which is how we secure the back end of all our big root keys and so on, can be supplemented by software version, which will make it a lot easier to scale and so on. So you can have an HSM lookalike that is actually built in software based on MPC. Same thing applies when you're terminating TLS. Instead of storing the private key on a server, you can separate that in 2 locations. So, you know, somebody has to hack into 2 different machines, for example, to get access to this. There are financial service companies now that actually are able to collaborate and build machine learning, for example, models between them without sharing the real data, because MPC can actually be utilized to run machine learning and maintain the data half encrypted, if you wish. Cryptocurrency transactions using MPC is a wonderful thing, because the signature depends on a private key, and if that private key is stored in 2 different places, then the opportunity for stealing that private key is much less. And managing confidential data encrypted at rest in general. Again, you know, if somebody wanted to attack any system, they would attack where the private key lives. Now, it's very interesting to note that the bad guys who wants to attack the ecosystem we have today are actually connected. They're working together in a very good way. And they support each other. They actually share a lot of things. But the good guys, quote unquote, don't actually do that. It's interesting. You hear about countries wanting their own internet that doesn't connect to others until you do something else. You hear about, how do I separate my network from others? And these are actually not exactly the right way to do things. It's starting from the lack of trust, because countries don't trust each other and competitors don't really want to work together all the time. So the result is sort of a backward world. You hear about countries wanting to have their own encryption methods, and using multiple encryption methods in one environment is not something that anybody has ever accommodated, because the current systems use the one set of algorithms basically. So the use of multiple algorithms does perhaps the protection of really sensitive applications. Now a country still wants to talk to other countries, so there still need to be a set of standards that everybody uses. And encryption, if done correctly, with sort of separate methods, could actually relax the dependency on this data residency issue we're dealing with today. The cons for this is, we're likely to have weaker algorithms, unfortunately, because standards get examined by everyone. They're out there being examined and everybody's looking at them. And it will complicate the world, because we do not know how to operate the world with multiple encryption methods. So there are changes that we sort of need to accommodate in our systems today. So how do we use cryptography needs to change. And I think part of how we change is to think of the weaknesses that we built over the last 25 years and try to accommodate what the needs are. The old way is basically hardwiring cryptography into everything, which made it harder to change things. You don't want the general population to modify cryptographic implementations because they probably do it wrong. But we do need to update things, and to update a cryptographic algorithm today, you need to basically change the entire software stack, because it's running at the bottom of hardwired in the middle. The new way needs to accommodate all the weaknesses. So agility is one. Fixing the issues that we've found over the last 20-some years is really important. And in my opinion, the most important issue is, how do we store our private keys? There are billions of private keys all over the world. And the reason I got excited when I started to talk to people about MPC was because that is actually the best method to store private keys, although there's a lot of other uses. But that's the best way to basically fix the most important security issue that we have in our implementations today. And then we need to know which algorithms. Now, MPC is dependent on the algorithm. So separating a key into two and being able to conduct a signature or an encryption operation using a particular algorithm. If we try to apply MPC, we have to be able to use a separate MPC construct for each algorithm effectively, and that will actually take a lot of work. We should actually be prepared before this quantum computing thing, if it were to happen, to how do we update the MPC implementations as well. But it's literally one of the, if you want to look at how do we protect confidential data today, there's the confidential computing that the hardware manufacturers supply, which is probably the fastest but the least secure implementation. MPC is kind of in the middle, which is it's fast enough, but it's and it could be, you could use machine learning algorithms on top of the encrypted data and so on. And then there is homomorphic encryption, which you could argue is more secure, but it's a lot less performance savvy. So the middle ground that MPC covers between supporting machine learning over encrypted data, storing all the private keys properly, and so on, is probably the best option at this point. And we've seen, a lot of the financial services companies support that. That's the end of my presentation. Thank you very much for listening. And Frank, I'll give it back to you.